Hey guys, this is Joseph from startdataengineering.com. In this video tutorial, we will look at three key techniques to optimize your Apache Spark code. Before we dive into those techniques, we will have a quick introduction of what distributed storage systems are, a quick introduction of what distributed data processing systems are, and then we will look at those three key techniques. As always, if you want to follow this in blog format, it is available at startdataengineering.com. I will attach the link in the description below. Alright, so the structure of this tutorial is going to be concept introduction. So we'll introduce a concept and then we will run some code examples on Spark. Then we will look at the Spark UI to see how that code was executed. And we will close off a concept with the trade-offs that we might have to make in a real life scenario. For setup, we are going to be using Amazon EMR, which is Elastic MapReduce. It provides us a way to easily set up a Spark and HDFS cluster. The link is in the description below. You can follow that, and that are steps that help you set up an AWS account and an AWS EMR instance. Alright, so let's get started. The first thing you'll have to do is SSH into your EMR master node. So if you have if you have your EMR set up, you will see the master public DNS here, which you could copy, and you could sign in using your pem file minus sde.pem, and it's Hadoop at the master DNS. So just like what's shown here, but make sure to use your master public DNS. So just type in yes, and we will use a terminal multiplexer or tmux because sometimes the connection dies off, so I like to keep my connections alive using tmux. You could also use screen, but I prefer tmux personally, and that's why I'm using tmux. So start a new session. Alright, so let's download some data. So you have the data available at Dropbox. It's public, so you can copy that. I should have copied this. This is difficult to type. So it's downloading a zipped file from my Dropbox, and once it's downloaded, we can unzip that and move that data over to our distributed storage system, which in this case is HDFS. We will see what that is in the next slide. Alright, so you can see the archive file is there. Let's go ahead and unzip that. So the archive file has data set for 2015 and a data set for 2016. They are parking violation tickets data. They are from Kaggle. Again, link to the data will be in the blog, so please check that out if you have the time. Alright, so it's unzipped. Now let's take a look at what our HDFS folder structure is. There's nothing there, so let's make a directory and just call it input. And you could use this copy from local command to move files from your local system to you can use, sorry, I missed the T there. You could use copy from local command to move files from your local file system. I'm using wildcard here to HDFS file system. So this will move 2015 and 2016 to input folder in HDFS. Alright, so let's see if it worked. Perfect, so you see both those files are in the input folder in HDFS. So when you want to access HDFS file commands, you use HDFS DFS for Hadoop distributed file system and then distributed file system. And similarly, you download another mapping dataset, for example, which maps the plate types to a description of that plate type. Again, we will see what these are soon. Alright, so you see plate type has been copied here. Same process. Let's make a mapping directory, and then let's move it over. Let's make sure it's copied. Yep, so perfect. So you have the files there. Now let's take a look at what distributed data storage systems are. Distributed data storage system is basically a cluster of machines, usually called as nodes, that are connected together, and it's used to store data that is too large to be stored in one machine. For example, if you have a data which is like 500 terabytes in size, you break them up into smaller chunks. These are called chunks or partitions interchangeably, and they're usually around 128 MB in size, and they are replicated 3 times, so there's always 3 copies of the same data chunk. Excuse me. This is because if 2 of the nodes fail in a cluster, you have a third node from which you could access the data. It is a fail-safe mechanism. This is a pictorial representation of what happens. So you have a 500 TB file, it gets split into chunks, and then it gets replicated across the nodes. So you can see like C1 is here, here, and here. And similarly, you could see other chunks being replicated as well. So that's what distributed data storage systems are. Let's understand what distributed data processing systems are. These are also called sometimes MPP, massively parallel processing systems. So they're used to process process data stored in distributed storage systems. So in traditional systems, what happens is all the data is brought to a machine where it's processed, and then some output is generated. But in distributed data processing systems, you have data separated out into chunks in different nodes in the cluster. The processing actually takes place locally on each node. Again, it depends on the complexity of the processing, right? For example, if you have a simple filter type processing, like you're just filtering a data set, it can be a local process. What that means is the data does not have to be moved between nodes. You can just filter it within the node. But if it's a wide transformation type process like group by or joins, what has to happen is you have to actually compare data set in the chunk in one node versus a chunk in another node, and that is called a wide transformation. You'll see an example in one of the sections below. And wide transformation is what we want to avoid. This wide transformation is sometimes called exchange because you're exchanging chunks of data between nodes. It is also called as data shuffling. In Spark plans, you will mostly see it being denoted as exchange. In blogs and such, people denote it as data shuffling. So they're basically the same. And with most optimizations, the idea is to reduce the amount of data shuffling, because data shuffling is one of the most expensive operations that can be performed on a distributed data processing system. And one thing to note is in this tutorial, we will be using Spark as a distributed data processing system. You can use Flink or whatever. The concepts still are the same. And we will use Spark data frames specifically because Spark data frames are a good layer of abstraction over structured data. And also it is automatically optimized by the Spark execution engine. You could also use RDDs, but then you will have to make sure it's optimized when you're performing any type of operations. Okay, so this is traditional data processing model where you have one machine and then you have some process just reading, for example, in this case, reading one line at a time, doing some processing, and then writing it to an output file. But this is a distributed data processing, so you could see like the process actually happens within the node, and then the data is written to the disk in that node. So now you have the process data here. So if you want to read process data, HDFS actually has that for you. So this is distributed processing. And again, this is a narrow processing because we are not transferring data between nodes, but we are only limiting the process within a single node. Okay, reducing data shuffle. This is the first technique that we are going to see in this tutorial. Basically, the entire idea behind all other techniques is to reduce shuffle. We want to reduce the exchanges, but sometimes exchanges are inevitable. It depends on your use case. Depending on your use case, you could choose to pre-process the data so that when you're actually running queries, you don't have to shuffle them. And if you're okay shuffling the data for one time, you don't have to pre-process them. So these are techniques. These are not rule of thumbs. These are just techniques. And depending on your code logic and how your data is going to be used and queried, just choose whichever one suits your needs. So let's consider the group by operation. So when you do a group by operation, what really happens is this. So let's consider the parking violation data set, right? So let's assume you have data sets in node 1 and node 4, and you want to do a group by plate type and sum the columns, right? So you can see the plate type MCD here and MCD there, but at the end you want MCD 2 here. It's actually supposed to be 2. You want this answer here. So now you're actually going to have to transfer this data from here to here, and then same from here to here. And similarly for other records as well. So this is called a white transformation because you see data flowing from node 1 to node 2 and node 3, and similarly data flowing from node 4 to node 2 and node 3. This is what we wanted to avoid. There is a way you could avoid repartition at group by time or data shuffle at group by time by repartitioning the data before you do the group by. So you might be wondering, hey, how is this different? You're still doing the data shuffle here versus here. The idea is if you want to do group by multiple times in this data model, you will have to do shuffle every time. But if you have it repartitioned already, any number of group bys will only be a local type transformation. So you can see here we land all the MCD types, AMB, LMB in one, and LUA and LOC types in another. So a group by will essentially just be internal or narrow. And again, there is this trade-off, right? You are doing the work beforehand, and then at query time, any number of group bys you run will always be a narrow transformation. All right, let's actually write some code. Let's start a Apache Spark shell. So I used to execute as basically 2 virtual machines to run our processes. So let Apache Spark start. Okay, sorry, I missed the S there. So it's starting. So this is called a Spark REPL, read, evaluate, print loop. You have this in Python and Scala as well. Basically, you can try out commands, do one command at a time. So let's create a data frame called Spark violations. So this comes with a Spark session variable called Spark. But if you're writing this as a script, you will have to create the Spark session explicitly. But since this is a REPL command line, we don't have to do that. It's already created for us. And let's look at this, right? So what's happening here? So we are saying Spark session read the CSV available in this location. So we have, remember, we have two CSVs available in this location, 2015 and 2016. Excuse me. And we say header is true because those files have header present. So it's reading. All right. So now let's do a group by. Plate type count data frame is Spark violations dot group by. Let's group by the plate type and get the counts. Very simple transformation or simple process. One thing to note about Spark is that it is lazy loaded. So what does that mean? That means when you do these commands, Spark is actually not executing these commands. It just knows that it has to do it. So it waits for a type of processing that requires it to do it. For example, when you want to write to an output, you obviously have to have the data to write to an output. So in cases like that, it will start the execution. So Spark is lazy loaded. So up until now, it has not executed. And you can actually type the data frame name and explain to see the plan that Spark will follow to execute internally and get this data frame for you. So basically it looks as it file scans it and then it aggregates it locally and then it exchanges, meaning data shuffle. This is the part we want to avoid, and then it aggregates again. So basically what's happening is, if you see here, it will do a mini optimization here to make sure a small group by is done here and then send over the data just to make sure the data size sent over the network is small or the data shuffle is small. So that's the plan that Spark is going to do. And note, Spark has not done this yet. It says it's going to do this. So let's actually make Spark do it. So let's write it, and the output format, let's keep it as CSV for now. People generally have some encoded format like Parquet, but for this simple example, let's keep it CSV. Let's say header true, and then we will do a mode of override. This override means you just override this location if there's any data available and already present. Not recommended for production use cases, but for our example it's fine. So Spark will actually create a folder called plate type count, and within that folder it will have those individual chunks of data that we talked about earlier. So let's see, plate type count, you're writing it to a CSV with the header true, and override it if any data is already present, and save it to this location in HDFS. So now it's actually starting the process. So it's starting to read, and then it'll do the hash aggregate, and then it'll do the data shuffle or exchange, and then another hash aggregate, and then it'll write to the HDFS file system. So it's actually not a large data set. I think it's about 3.8 or 4 gigabytes, so it's quite fast. Let's exit this. Now let's see how to view this in Spark UI. So if you go to your EMR console, you could actually go to Application User Interfaces and then click on Spark History Server. You could also see it through here, but I prefer to do Spark History Server because you can actually see the DAG and it's easier to understand in my opinion, but you could do it through here as well. You could just click on the application so you could see, like, sorry, it's loaded and not ready. Sometimes you have to give a few minutes for this to show up. So let's see. Alright, it's here. Let's click on it. Yeah, so sometimes you have to just give it a few more minutes for it to show up. So if you see a server error or something like that, just give it a few more minutes. You can view it through here. So you can see only CSV is succeeded. CSV is basically it's this command. So we want to wait for the write to show up here, or I think it'll show up as save, and then we can look at the UI. The UI it's quite slow, mostly because the type of machines we have is very small, and it's not enough power to run a data processing framework like Spark. Alright, so while it's loading, let's move on. So this is pre-optimized, so you are just grouping by, it'll cause a shuffle, right? So let's take a look at this. It's the same thing, but we have an additional step where we repartition 87 plate type. So you might be wondering what 87 is. 87 is basically the number of unique plate types in this data set. I got that data beforehand, but you might want to figure it out yourself by doing a group by on plate type or distinct and counting how many unique values are there. So, alright, let's see if this has shown up. Alright, so it's shown up here, so let's look at the server. Excuse me. Okay, perfect. So you can see the job and the application ID here is 001. You'll be able to see it here as well, 001. So here, if you go to the SQL tab, you will be able to see CSV and save. I find the SQL tab easier to read than the jobs tab. So let's look at the CSV tab. Basically, it's just reading file, reading scan. Just that's it. If you look at save, you can see this whole DAG here. So it's scanning the file. There are 22 million rows, and then two files, which is 2015.csv and 2016.csv. It is doing a local aggregate, so it will try to pre-optimize it and do some local aggregate, and then it exchanges the data, which is the data shuffle, and then it does a final aggregate after making sure all the group by fields are in one executor, and then it writes it into HDFS. So if you look at jobs, you can see it in more detail. Right? Click on the stack. You see, like, there is the stage 2 and stage 3. There is a line between those two. That is the shuffle part. And it says skipped already because it did it as a separate job. That's why it shows it skipped. That's why I prefer to look at the SQL tab because it's more easier to understand. Alright, so you see exchange happening and then aggregate. So aggregate locally, exchange, and then aggregate finally across data from all the nodes. So let's see how we can optimize this, right? Basically, we are repartitioning by plate type field, and we are repartitioning it into 87 chunks. 87, as I mentioned earlier, is the number of unique plate types, and I got this beforehand by doing a group by and figuring out how many distinct types of plate types are there. So let's go ahead and try this out. So Spark violation, you could just do the up arrow key and it will give you the previously run command. So I'm reading in data from input folder again. Spark violations. So let's do a repartition. Spark violations dot repartition. So repartition to 87 chunks based on plate type. So what this will do is they'll split up the Spark violation data frame into 87 partitions, and it will use the plate type field to split data into those 87 partitions. So now all the plate types of a specific type are within a specific partition of this 87. So let's see what this explain for this data frame looks like. So it's scanning, exchanging based on hashes. That's it. So the next step would be similar to our previous example. Data frame dot group. So we are again doing the group by, but this time on the repartition data frame. Oh, sorry, why is caps there? Alright, so now let's take a look at how this is going to be executed. So you see file scan, again you see the exchange, hash aggregate. So this might be a little bit confusing. You might be wondering why we have this exchange again. But remember, Spark is lazy. So what it's actually doing is when you do a plate type count df.explain, it actually figures out all its dependencies. So these two steps are actually the steps you saw earlier when you were trying an explain of the Spark violation plate type data frame. So you see file scan and exchange. Those two steps are these, and then you'll do hash aggregation internally for the group by. Let's go ahead and write it to an output to see how it looks like. It's the same plate type count data frame. You're writing to this location, you're overwriting an already existing data set. That's fine for this use case, saying header is true. Alright, so now Spark is actually going to do the repartition, and then it will do the group by, and then write to your HDFS file system. The repartition will be expensive for the first time, but consecutive group bys will be faster. So it's basically a trade-off between doing the group by earlier and having the data in a form that is easier to be processed, or having to reprocess it each time. Alright, that was fast, so let's exit this. Let's see if it shows up here. So you will see this time it's showing up as application 002. Each Spark REPL session, from the moment you open it till you exit, will be considered a separate application in this. So let's again go to the history server. So I'm going to 2 because that's what we currently ran. Okay, it's still showing running save as running, which is not really the case because it finished here. It's just waiting for the driver to send the relevant information. It takes quite a bit because the systems are not powerful. Let's wait for a bit here. And in the meantime, let's see what the trade-offs or takeaways are. So the takeaway is data shuffle is expensive, but sometimes necessary when you're doing like group by or joins or things like that. But what you could do is you could use this idea of repartition to get your data ready for any number of group bys that may occur in the future. So if you're having to do multiple group bys in the future, you could do repartition once and avoid all the repartitions later. And it's always good practice to check explain first, because with the explain you can actually see what Spark is going to do before actual execution, because in the UI you can only see it after the code has executed or during the execution time. Let's see if it came back up. Alright, so you can see CSV and save. Let's look at save. Alright, so here you can see exchange here, right? So this is the repartition. So you can see, like, if you read it carefully, it says exchange hash partition, plate type, 8713 I think is the number of the column, and 87 is the number we specified in our repartition command. So it does the exchange first and then the hash aggregates. So the next time you do this, you won't have to do the exchange, it'll just be this part, these hash aggregation parts. So that's data shuffle reduction using repartitioning technique. So let's go on to the next one. The next one is caching. So in Spark, what happens is when you do any data processing, it reads the required data from HDFS in our case, or any distributed storage. It does some processing in memory depending on your logic, and then it writes it out to the disk. Caching is a technique where you could say, you could ask Spark to keep a data frame in cache forever or specified amount of time, so that you don't have to read it from from the disk each time. What does this mean? Let's look at it in detail. So let's look at one node in our cluster. Let's assume we are using some process to go from C1 to C1 process and so on, right? What happens is Spark first reads file from the disk storage, and then in memory it does some processing and then writes it to disk storage. But let's assume you want to use this C1, C2, Cn chunks multiple times. So let's say you want to produce this processed files based on one logic, and then another set of process files based on another logic. You want to keep this data frame in memory so that you can skip this whole work of reading it from disk storage, which is expensive as well. So let's again look at it with an example. We are going to be following the same example that we saw earlier. So you could see, like, the same thing we did, repartition group by, and we are writing it. Right. So we are in Spark. We are reading it from a CSV location, putting it in Spark violations, and then we are repartitioning it, and then we are doing a group by, and then we are writing it to a HDFS folder at plate type count. Right. So here we did a count, but let's assume now that we want average. It should essentially be just reading data from that repartition data set. So let's see how that works. So writing to the file. Alright, it's done. So instead of count, let's do average and just rename it to this data frame to AVG. Rename it to AVG. So we are writing it so that the actual execution gets done. Again, here average is not meaningful or anything. It's just a simple aggregation command we are using as an example to understand how to use caching and why we want to use caching sometimes. Alright, so let's wait for it to show up. Alright, and it showed up here. So let's look at our history server. Yeah, sometimes it shows up in completed, sometimes in incomplete. So again, history server, it's not optimized right now, so it's a little bit slow, which is fine for this toy example. Let's wait for a few more minutes. It's kind of annoying, but because we are using really low power machines, like I'm just using M5s, which are I think one of the cheapest ones available. You could use something similar, but one thing to note is always use two, because if you use one, it doesn't seem to be working right. Alright, let's wait for a few minutes. So by this logic, you would assume when you're calculating plate type average data frame, it will automatically use this already repartitioned data frame, but it actually does the whole repartition all over again because the data is not cached or saved to any disk file system. Alright, I think it's finally there. Alright, let's look at SQL. So we have two save. One for plate type count data frame and the second one for plate type average data frame. So let's look at the plate type count data frame save method first, this one. So you see what we saw in our previous example. You scan the file, exchange it based, which is basically the partitioning step based on plate type and 87, and then do the hash aggregate. Second time, you see the hash partitioning happening again. This is not what we want, because we want to not do the exchange, and that's the whole reason we were repartitioning that data set. So let's see how we could do that. This is the kind of the same code, but with this additional step where we cache the data frame that was partitioned. Instead of using the partition data frame directly, we are caching it as cache data frame, and then using that cache data frame to skip the partition step the second time. So let's see how that works. Again, this is all written out and available in my blog post, which is I attached the link in the description below. Feel free to check that out as well, because that might be easier if you want to follow along slowly or pick up at arbitrary locations. So let's start from the first. We are reading in the input folder into Spark violations, and we are going to repartition it by plate type. And this is the interesting part, we are caching it. So we just say, and when we are caching it, it is good practice to only cache the columns necessary. By default, this data frame is very wide and has a lot of columns, but since we don't require any other columns, we only cache the column that's required. And plate type. And now we do our group bys, but use the cache data frame instead. Just close. Oh God! Again, the Y. All right. So now let's write it to this location in HDFS. So what Spark is doing right now is actually repartitioning it, and then it's also caching the repartition data frame in memory, and then doing group by from the data frame in memory and writing that output to a HDFS location which we specified here. So now let's calculate the average. So instead of directly using the repartition dataset, we use the cache data frame. And similarly, we just write it to a HDFS location. If you notice, the second time was much faster. That's because we already have the data frame in memory. Let's exit and take a look at the Spark UI, see if it has shown up yet. Let's give it a few minutes. In the meantime, let's look at some takeaways of caching. So basically, the idea is if you're going to be using a same data frame over and over again with multiple different types of transformations, it's a good idea to cache that data frame in memory. But one thing to be aware of is that if the data frame that you're going to cache is too large, it's going to get really unwieldy, and your Spark's memory will be constrained by that. And you might also consider only caching the data frame columns that you need. And if you want a combination of cache and disk storage, you could use this method called persist, where you can specify how much of the data to store in cache and what percentage to store in disk and other variations. So those are some things to consider. Let's look at the history server, see if it showed up yet. Give it a few more minutes. You could look at the yarn applications that are running. Yarn is basically a resource negotiator for HDFS. It makes sure that the nodes have enough memory and keeps track of which nodes are free and which nodes are dying and things like that. So you could actually look at this application list on the UI on the command line as well. You'll see nothing is active, but it's not being reflected here. Alright, so it showed up as succeeded. Let's see if it showed up here. We want application number 4. Alright, it has showed up here. Okay, so let's go to SQL. Again, the first save is for plate type count data frame. The second save is for plate type average data frame. Let's look at plate type count data frame save. You will see the same exchange, but this time you're keeping it in memory. It's quite a large table, but because we're only using one field, it shouldn't be too big. And then this aggregate, which is the group by, is reading from that table which is already in memory and writing it to HDFS. Let's look at what was done for average data frame. So you can see this is all skipped. That's why it's like it doesn't have any metadata. And you could see like in memory table scan and just writing it to HDFS. So this is local transformation only. You can look at it in detail here. So you'll see, if you look at this, you'll see the first stage has been skipped because you already have data in memory. So that is the effect of using cache here. Alright, so the last technique is actually two, but it both involves the join processing logic, so put it as one technique. So join strategies. In any types of data processing, joins are crucial. We do it all the time. So there are some ways you could optimize joins, because without optimizing them, they are going to be data shuffled all the time, except in very specific scenarios. Alright, so let's take a look at joins, right? So let's say you have two data sets which has plate types and some other columns, plate type and some other columns, and you have a mapping, or you call this dimension, in data warehousing, you call this dimension and you call the big table fact table. So you're basically joining this dimension table against this large fact table. If you join it without optimizing, you will end up shuffling both the dimension and fact table data sets. So it's a very large and expensive job. So that's join. Right? So let's see a way you could negate this. So as I mentioned earlier, in data warehousing, you have a large table, usually called a fact table, and you join, this fact table has like IDs, and dimension tables has like the name of those IDs or description of those IDs. So a common scenario is where you join these fact tables against dimension tables. In this scenario, if the dimension table is small enough, instead of transferring the fact table across the network, you could actually move the dimension table to every node where there's a chunk of the fact table. This way you're only moving the small data frame and you're not moving the large data frame across the network. This is called broadcasting because you're essentially broadcasting the dimension table to different nodes in the cluster. And by default, Spark tries to do a broadcast join if your table size is less than 10 megabytes. If it is not, you could hint Spark to use broadcast join. So let's see how that would work. So here you see similar setup as on the join before, but in this use case, you're just directly joining only the small data set is being transferred. The large data set is kept within the node or local transformation. All right, so let's look at an example. Let's go here. So because our data may be growing, it's good practice to remove your HDFS files. Again, don't do this without caution. Again, in real life scenario, you don't want to be deleting data without caution. Let's start PySpark. This time we will read 2015 into a separate data frame and 2016 into a separate data frame. Let's call that, I don't want to type the whole thing, so I'm just going to call it P15. These code examples are available in my blog if you want to copy paste it, but I find it better when you type it out yourself. So again, same type of CSV reading we saw earlier, but this time instead of reading directly from a folder, we are reading a single file individually. So this will just read the 2015.csv file, and similarly we do 2016. I'm going to rename a column just because it's easier to join on, but doesn't really matter that much because it's just the metadata renaming. Do the same for 2016. These are quite large data sets with data skew. So what we are going to do is we are going to make sure that we only do this operation for a play type called COM. This is purely just to get this example to run faster. If you're trying this or following along, please feel free to try it without this filter and see how it performs. So if you can see here, it's basically filtering 2015 for and keeping only records which have play type of COM. We similarly do same for 2016. Gotta change this too. Alright, so now let's join them. Let's call it join data frame P2015. COMS cabs. Doing an inner join and only selecting certain columns for the output. Let's look at explain. This is quite large, so I'm gonna enlarge this. Okay, so you see here it's called a sort merge join. Basically what is happening is your file scanning 2016's data, filtering it, making sure it has only the COM play type and it's not null, and then you're exchanging it and sorting it, and you do the same for 2015 data as well, and then once both those data sets are available, you merge it. I'm not going to do this because this is a very expensive operation and it will take a long time, so I'm gonna skip it for now, but we can look at the Spark DAG that will show up if we actually did it. It's right, this is from my blog, so it'll look something like this. You could see 2015, 2016, and then both of them being shuffled. More clearly here, you see like I think this is 2015, this is 2016, and then you do exchange, and then you have sorted, and then you merge it, which is a very expensive operation, and so I'm not going to do it now. But if you're following along, please feel free to try it. It might take a while, but it'll be a good learning experience. Let's go ahead and look at this scenario where we do a broadcast join. It's very similar to what we are doing, but if you look at this, we are hinting broadcast. And because we are broadcasting, we try to limit the columns in the data frame to only the required columns from both the data frames. And then we broadcast one of the data frame, and then we do the join. So let's go ahead and try it out. I'm gonna make this smaller so you can follow along. So P most of it is from the previous thing, so I'm just gonna use that P2015. And then P2016. We're using the same COM filter, but this time we have a additional scenario where we only want play type and summons. It's always good practice to only process or keep in memory the columns you need, because if you keep unnecessary columns, it's going to limit your performance. What is it? It says it doesn't have plate. Oh, yeah, I didn't rename the columns, so let's rename the columns. and from 16 we only need the issue date. You can see why from the join condition. Alright, so here we cache them just so it's easier for the execution engine to do it. And if you want, a cool thing is if you do count, doesn't work often because Spark optimizes it sometimes, but if you do count, the execution actually happens. So it's actually being cached right now. Very small data set, only 1,000 records. Okay, so you can see 2015 is quite large. It has, I mean, it's not super large, but it's much larger compared to 2016. So this will give you an idea of which table you want to broadcast. The answer is 2016. So let's go ahead and do that. So let's create a join data frame is equal to 2050. So if you look at this, we are typing something called hint broadcast. So this will hint and let Spark know to send this table out as a broadcaster table. And then we define the join conditions. And what type of join it is. And then what columns we need. Can't extract summons number. Did I mistype it? Oh, there we go. Alright, I missed this this comma. Let's write it to actually execute the broadcast join. Or let's look at the explain first before that. Alright, that's quite a big one. So what's happening here? So you can see in memory relation, up until that is the caching thing. So it's actually reading it, filtering it by com, and then aggregating it, hash partitioning it, and then this is it's keeping it in memory. So if you look at the code, what's actually happening is the distinct will cause a repartition. That's the hash aggregate here, and then you are caching it. Because we are using distinct, that ends up in an exchange, which is fine for our example. And this is the same thing will be repeated for 2015's data frame. So if you look at this, 2015, and then at the end you do a broadcast hash join. Let's go ahead and write it out and see how it shows up in the Spark UI. It is actually doing all the steps right now. We don't really need to cache it here. I just cached it because if you want to try multiple types of join, it'll be easier. But you could skip that as well if you don't want to cache it. And the distinct, I chose distinct because it reduces the size of the dataset. Because without distinct, the dataset will be millions of rows in length. You may want to try to optimize that as well. Think about how you could optimize the distinct so it doesn't involve a lot of data shuffles. So while it's executing, let's look at some takeaways. The main takeaway is one of your data frame has to be small, and when you're broadcasting it, try to make sure you're only broadcasting the required columns, not all the columns in any data frame. It's taking a while. Let's see if it showed up here. Let's see if it showed up in the history server. If our history server is optimized, it'll actually show the UI while the code is being executed, but for some reason it's not showing, so let's wait for it to finish. So the write has complete. Let's go ahead and take a look at the UI to see the Spark execution plan. Let's go there. It was application number 6. Let's go to SQL. Let's look at the save method because that's the last method that we were executing. Alright, so you can see a whole bunch of stuff, but basically up until here is the steps that were prior to caching. So what happened was it read from a CSV and filtered by play type, selected only play type and summons from 2015, play type and issue date from 2016, did a distinct. That's all here. That's this exchange. And then it kept the table or data frame in memory using the cache. And then this is the part we are interested in, where you're doing a broadcast exchange. So it chose to exchange the data frame with 1100 records into this data frame with 2 million records. So in this case, only the small data set is getting shuffled across the network, greatly reducing the cost of data shuffle in this case. So that's how you could do broadcast joins. So let's go to the last strategy, which is bucketed join. So we have seen how you could join a large dataset with a small dataset. You could do broadcast join and just broadcast one small dataset over the network. But what if both the tables that you want to join on are huge? In this scenario, it looks something like this. It's a very, very extremely expensive operation because you'll essentially have to shuffle two large data set across the entire cluster, which is very problematic. So you could use a technique called bucketing. It looks something like this. It looks complicated, but it's not that complicated. So what bucketing is, you could partition two data sets based on a field or column, and you could use these things called buckets so that both your data frames file chunks which have the same fields are in the same nodes. And this works because bucketing is based on the hash of the field in which you are bucketing, with which you're bucketing by. So basically, if you look at this, right, so what happens is you look at MCD and you'll create a hash, and that will determine this MCD should live in this node. And similarly, you'll get the same hash for MCD because hash is going to be same for the same keys, and we'll figure out this key should live in this node. So even though these data frames are independent, the way they are co-located will ensure that any operation that you do on that field amongst those two data sets will be local. So you can see this blue outline. That's the bucketing part, which is again expensive, just like shown here, but without the join. So that's a little bit less expensive. So once it's bucketed, you could do a join which will become a narrow transformation. Similar to caching or similar to repartitioning, this is useful if you are going to be doing multiple multiple joins later on, and it's also useful when just doing joins, because sometimes doing joins and shuffling two large data sets is a lot for the cluster to operate on. Let's take a look at an example. So I'm not going to do the pre-optimization, that is the same implementation without the bucketed join, because it will take a long time and it may crash given the size of our executors. But we can take a look at this code. Not going to execute it because again this will take about 30 minutes, but you can try it out when you're following through. One thing to note here is when we're starting PySpark, we usually only specify number of executors, but in this case we are specifying the executor memory. This is because this is a high memory requirement operation, because joining two data sets you have to keep a lot of data in memory, and that's why I have to increase the executor memory to 8 gigabytes. So let's go this code. So similarly, reading in 2015-2016 into data frames. This is just a simple trick to change the column names, because all the column names in 2015 and 2016 have spaces, so we just replace them with underscores. And this time we make sure it's only COM and the vehicle year is 2001. Again, this was purely to make sure that this could be done in a certain amount of time, because without these filters this time might go up significantly. And we also let Spark know not to do broadcast join. -1 means disable broadcast. This is the configuration to allow broadcast joins automatically by Spark Optimizer. And then we bucket by, this is the main thing. So what happens here is you take this data frame and then you split it up into 400 buckets, which are partitioned by vehicle year and plate type, and then you save that as a table. So internally what is happening is you will have 400 buckets within which the partitions are decided by the hash of these two fields, and then it will be saved to HDFS folder as a table, which basically means it will be saved in a HDFS folder called spark/warehouse. And this is a common technique where you can save it as a table here, and then another Spark application can directly just read the table using this API where you just say Spark read table. And join, it's very similar. You're taking 2015 data frame, joining it with 2016 on plate type and vehicle year, and then you're only choosing summons number and issue date. If you explain, you will see a sort merge join, and if you do that, it'll take quite a bit, but it will complete. So let's look at the DAG here because we're not executing it. So it's the same code as I was showing you. Basically what will happen is you will, after saving the file, this was the join command. So this is basically the table 2015, this is the table 2016, and then this all happens without any exchange, so it's pretty efficient. Some of the key takeaways with bucketed joins are it's okay if you want to pre-shuffle the data so that in the future you don't have to keep shuffling it for each join, but if you're only doing one join, it might not be worth it depending on your use case. The other thing to be aware of is bucketing works really well with discrete columns, columns such as play type, be clear, etc. But it does not work very well with continuous columns like I don't know, product price or stock price. In those cases, you might want to do something like a histogram blocks where you like specify a block of the data into one bucket or a range of prices into one bucket and so on. So that's bucketed joins. So with that, we come to the conclusion. The general trend or the general idea that should be at the back of your mind is you want to reduce data shuffle when you can, and use caching if you want to and if you can, and optimize join again to reduce data shuffling. And these are all just techniques and not rule of thumb. You should know that these techniques exist, and depending on your logic, you may or may not want to use them. For example, caching may not always be necessary. For example, if you're only doing a operation once on a data frame, you don't have to cache it. You could just do that operation once. So know these techniques and use them when it adds benefit to your processing. These techniques usually account for most of the issues that I have seen personally with Spark optimization. As I mentioned earlier, knowing when to use them and when not to use them is very crucial. There is one more technique I wanted to talk about, but I didn't in this post. It's key salting for data skew issues. We will talk about that in a future video or blog post. But just to close off, the fundamental concept is the trade-off between pre-processing the data and preventing data shuffles in the future, or vice versa. Hope this video tutorial gives you some ideas about how you could optimize your Spark code and how you could start thinking about data processing frameworks. Let me know if you have any questions or comment in the comment section below. You could put your questions in the comment section below, or you could put your questions in my blog, whichever works for you. To close off, this is a lot of fun making this video. Hope you learned a lot and hope you had fun too. If you found this article helpful, please feel free to like, share, and subscribe, and hit that notification button. It really helps me a lot. Yeah, and until next time, thank you.